Close your eyes for a moment. Imagine standing in the most remote place you can think of, perhaps the middle of the Sahara Desert at midnight, or adrift on a life raft in the Pacific Ocean, thousands of miles from any shore. Now multiply that isolation by infinity. Remove the sand, the water, the air, the warmth. Remove everything. What you're left with begins to approach the reality of the universe beyond our tiny blue planet. Welcome to a journey into the void, the cold, dark, impossibly vast emptiness that makes up nearly everything that exists. This is a story about nothing, and yet it's one of the most profound stories we can tell. Because to understand emptiness is to understand just how rare, how precious, and how utterly improbable everything we know and love truly is. I'm going to take you on a journey outward, from Earth to the edges of the observable universe, and we're going to confront a truth that both humbles and terrifies. We live on an impossibly rare island of matter and energy, surrounded by an ocean of nothingness so vast that our minds can barely grasp it. But here's what makes this story worth telling. This emptiness isn't just absence. It's a canvas, a stage, a fundamental part of what allows stars to shine and life to exist. The void is not our enemy. It's the reason we're here at all. Let's begin. Leaving home. We start our journey where all cosmic journeys must begin on Earth. Right now, as you listen to this, you're surrounded by matter. The air in your room contains roughly 25 septillion molecules per cubic meter. That's a 25 followed by 24 zeros. You can't see them, but they're there. Nitrogen, oxygen, carbon dioxide, water vapor, all bouncing around at hundreds of meters per second, colliding with each other millions of times every second. This is normal to us. This is what we call empty space, a room with nothing in it but air. But by cosmic standards, this is incredibly, almost incomprehensibly dense. Let's leave Earth's surface. As we rise through the atmosphere, something interesting happens. The air gets thinner. At the peak of Mount Everest, there's only about a third as much air as at sea level. This is why climbers need oxygen tanks. There simply aren't enough molecules to breathe. Keep going up. At the edge of space, roughly 100 kilometers above Earth's surface, the air has thinned to almost nothing. We're in what scientists call the thermosphere, where the International Space Station orbits. Here, in each cubic meter, you might find only about 100 billion molecules. That sounds like a lot, but it's 100 trillion times less dense than the air at sea level. The astronauts on the ISS float in what we call the vacuum of space. But even here, we haven't truly reached emptiness. There are still molecules, mostly hydrogen and helium, with traces of oxygen escaping from Earth's upper atmosphere. If you were floating here without a spacesuit, you'd die within seconds, but not from the vacuum itself initially. You'd die from the lack of oxygen, from the extreme cold on the dark side, from the radiation. The emptiness here can still conduct heat. It's not empty enough. We need to go farther, interplanetary space. Let's travel to the space between Earth and Mars. This is what astronomers call interplanetary space, and it's the first time most people encounter what they think of as real emptiness. Out here, roughly 150 million kilometers from the Sun, floating in the blackness between worlds, we find something genuinely sparse. In each cubic meter of interplanetary space near Earth's orbit, there are approximately 5 million particles. 5 million sounds like a lot, until you remember that the air you breathe contains 25 septillion molecules in the same volume. We've gone from incredibly dense to almost nothing in the span of a single astronomical unit. But here's what's fascinating. This empty space is anything but quiet. The Sun is constantly screaming into the void, ejecting a stream of charged particles called the solar wind. These particles race outward at speeds of 300 to 700 kilometers per second, carrying with them magnetic fields and energy. This is space weather, and it fills the solar system with invisible currents and eddies. If you were floating here, You wouldn't feel the solar wind. Directly, the particles are too sparse, too small. But if you had the right instruments, you'd detect it immediately. You'd see electrons and protons streaming past you by the billions every second. You'd register magnetic fields twisting and writhing. You'd be buffeted by shockwaves from solar storms. This is the important thing to understand. Emptiness in space is relative. Even here, in what seems like perfect vacuum, there's activity, there's energy, there's something, but we're still in the sun's neighborhood. We're still in the relatively crowded space near a star. To find true emptiness, we need to venture much, much farther. The interstellar medium. Now we leave the solar system entirely. We're traveling at impossible speeds, faster than any spacecraft humanity has ever built, heading toward the nearest star, Proxima Centauri, a red dwarf 4.2 light-years away. The journey would take thousands of years with our current technology, but we're making it in moments. As we leave the sun's influence, something dramatic happens. The solar wind, which filled the space around our star, begins to falter. We cross a boundary called the heliopause, where the sun's influence ends and true interstellar space begins. The Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. It's still out there, tumbling through the dark, sending back faint signals that take over 22 hours to reach Earth. This is the interstellar medium, the space between the stars. And this is where we encounter our first taste of genuine cosmic emptiness. In each cubic meter of interstellar space, there are approximately 1 million atoms. 1 million. Remember, that's compared to 25 septillion in Earth's atmosphere. We've reduced density by a factor of 25 million trillion. If the air in your room were this thin, you could count every single molecule in a space the size of a football stadium. And yet, remarkably, this isn't truly empty either. Astronomers have discovered that interstellar space is filled with all sorts of interesting things. There are clouds of hydrogen gas, some cold and dense, others hot and diffuse. There are molecules, simple ones like carbon monoxide, but also complex organic compounds, the building blocks of life. There are dust grains, microscopic particles of silicon and carbon, and ice, leftovers from dead stars. In some regions, the interstellar medium is almost thick with this material. Molecular clouds, the stellar nurseries where new stars are born, can contain thousands or even millions of atoms per cubic centimeter. By space standards, these clouds are practically solid. They're so dense that they block starlight, creating dark patches against the Milky Way that ancient astronomers thought were holes in the heavens. But in other regions, in the bubbles blown by supernova explosions, in the voids between spiral arms, the interstellar medium thins to almost nothing. In these cavities, you might find only 1 atom per 10 cubic centimeters. That's emptier than the best vacuum chambers we can create on Earth. Picture yourself floating in one of these voids. You look around, and you see stars, thousands of them, spread across the black dome of space. But the nearest star is light years away. The light you're seeing left those stars years, decades, even centuries ago. If those stars winked out right now, you wouldn't know for years. You are truly, profoundly alone. And this is still just our galaxy. We're still in the Milky Way, still surrounded by hundreds of billions of stars. We haven't even begun to approach the real emptiness between the galaxies. Let's accelerate again, traveling now at speeds that make light itself seem slow. We're leaving the Milky Way, rising above its disk, watching it shrink from an infinite ocean of stars to a pinwheel, then to a smudge, then to a point of light. As we climb away from our galaxy, the last tendrils of matter fall away. We're entering intergalactic space. And here, finally, we encounter emptiness on a scale that defies human comprehension. In each cubic meter of intergalactic space, there is, on average, less than 1 atom. Less than 1. You could scoop up a volume of space the size of a house, and on average, you'd find fewer atoms than there are people in a small town. This is a vacuum so perfect, so complete, that nothing we can create on Earth comes close. Let me put this in perspective. The best vacuum chambers we can build on Earth can reduce pressure to about 10 trillion molecules per cubic meter. That's phenomenally empty by terrestrial standards. You can do exotic physics experiments in vacuums like that, but it's still 10 trillion times denser than intergalactic space. If you wanted to create a volume of true intergalactic vacuum in a laboratory, you'd need a chamber the size of a planet, and you'd have to somehow remove every single atom except one or two. This is the universe at its most fundamental. This is what normal looks like on cosmic scales. The stars, the galaxies, the planets, the people, we're the anomaly. We're the weird, dense clumps in an ocean of nothingness. And this ocean is vast. The distance between galaxies is measured in millions of light years. Our nearest large neighbor, the Andromeda galaxy, is 2.5 million light years away. Light from Andromeda takes 2.5 million years to reach us. When you look at Andromeda in the night sky, you're seeing it as it was before humans existed, before our species walked the Earth, and Andromeda is close. The average distance between galaxies in the universe is more like 10 million light years. In the great voids, the massive bubbles of empty space that thread through the cosmic web, you can travel for hundreds of millions of light years without encountering a single galaxy. Imagine that journey. You leave the Milky Way and you point yourself toward the nearest galaxy cluster. You travel at the speed of light, the fastest speed possible, the speed at which causality itself propagates through the universe, and you travel for 10 million years. Every second, you cover 300,000 kilometers. Every year, you cover nearly 10 trillion kilometers. And for 10 million years, you see nothing. The galaxies behind you fade to invisibility. The galaxies ahead remain invisible. You are surrounded by perfect, absolute darkness, broken only by the faint glow of the cosmic microwave background, the afterglow of the Big Bang itself. This is the true face of the universe. This is what dominates existence. Not stars, not galaxies, not matter, emptiness, the temperature of nothing. But this emptiness isn't entirely cold and dead. Even in the darkest, most remote regions of intergalactic space, the universe maintains a temperature. And that temperature tells us something profound about the history and fate of everything that exists. The cosmic microwave background radiation bathes all of space in a faint glow. This radiation is the cooled remnant of the hot, dense early universe. Roughly 13.8 billion years ago, the universe was unimaginably hot, trillions of degrees. But as it expanded, it cooled. The radiation from that early fireball has been stretched by the expansion of space itself, redshifted from visible light down to microwave frequencies. Today, that radiation has a temperature of 2.7 Kelvin. That's 2.7 degrees above absolute zero, the coldest temperature theoretically possible. In Celsius, that's minus 270 degrees. In Fahrenheit, minus 454 degrees. To give you a sense of how cold this is, liquid nitrogen freezes at 77 Kelvin. Liquid hydrogen freezes at 14 Kelvin. Liquid helium, the coldest substance we can easily produce on Earth, freezes at 4 Kelvin. The cosmic microwave background is colder than any naturally occurring substance we know of. It's so cold that if you could somehow transport a thermometer to intergalactic space, it would measure the coldest temperature it's possible to measure. And yet, this radiation is everywhere. No matter where you go in the universe, no matter how far you travel, you cannot escape it. It fills every cubic centimeter of space with photons, particles of light that have been traveling since the dawn of time. There are approximately 400 million cosmic microwave background photons in every cubic meter of space. 400 million. That sounds like a lot, and in some sense it is. It's far more than the number of atoms. But spread across the vast scales of the universe, even this is sparse. These photons are so spread out, so diffuse, that they carry almost no energy. They're the whisper of a universe that was once screaming. This is what makes intergalactic space so cold. There's nothing there to hold heat. Heat is the vibration of atoms and molecules, the kinetic energy of matter. But in a place where there's less than 1 atom per cubic meter, there's almost nothing to vibrate. You could release a tremendous amount of energy, say, from a nuclear explosion, and it would dissipate almost instantly, radiating away into the void, absorbed by nothing. In fact, this is one of the strange paradoxes of space. In the thermosphere of Earth's upper atmosphere, temperatures can reach 1500 degrees Celsius. That sounds incredibly hot, and in one sense it is. The individual molecules are moving very fast. But if you were floating there, you wouldn't burn up from the heat. Why? Because there are so few molecules that they can't transfer their energy to you effectively. You'd lose heat through radiation faster than you'd gain it through conduction. The same is true in intergalactic space, only more so. The temperature is effectively the temperature of the cosmic microwave background, 2.7 Kelvin, because there's nothing else to define it. No matter to carry heat, no atmosphere to trap warmth, just the faint, cold afterglow of creation, the expanding void. Now we come to perhaps the most unsettling aspect of cosmic emptiness. It's getting worse. The universe isn't just empty, it's becoming emptier. And this emptiness is accelerating. In 1998, astronomers studying distant supernovae made a shocking discovery. They expected to find that the expansion of the universe was slowing down, decelerated by the mutual gravitational attraction of all the matter in the cosmos. Instead, they found the opposite. The expansion was speeding up. This discovery won the Nobel Prize and upended our understanding of the universe. To explain it, physicists had to invoke something called dark energy, a mysterious force that seems to be embedded in the fabric of space itself. The more space there is, the more dark energy there is, and the more the universe accelerates. What this means is that the distances between galaxies are growing, and they're growing faster and faster. Galaxies that are far enough away from us are receding at speeds greater than the speed of light. Not because they're moving through space faster than light, that's impossible, but because space itself is expanding between us and them. And here's the crucial point. There's a distance beyond which galaxies are receding so fast that light from them will never reach us. This is called the cosmic event horizon, and it represents a fundamental limit to what we can ever observe. Galaxies beyond this horizon are forever beyond our reach, not just physically, but informationally. We can never know what's happening there. We can never see them. They might as well not exist. As time goes on, this horizon shrinks. More and more galaxies slip beyond it. In the far future, trillions of years from now, only our local group of galaxies will remain visible. The Milky Way, Andromeda, and a few dozen smaller galaxies will merge into a single giant elliptical galaxy. And beyond that, nothing. Perfect darkness. The cosmic microwave background will have cooled to nearly 0 Kelvin. The universe will be cold, dark, and empty beyond anything we can imagine today. Eventually, even the stars will die. The last red dwarfs will flicker out after trillions upon trillions of years. Black holes will evaporate through Hawking radiation over timescales so vast they make the current age of the universe seem like an eye blink. And what will be left? Nothing. Absolute nothing. A cold, dark, expanding void, growing emptier forever. This is the heat death of the universe, the final state predicted by thermodynamics. Maximum entropy, perfect equilibrium, and perfect eternal emptiness. The meaning of the void. So we've taken our journey into the void, and we've seen the universe for what it truly is. A cold, dark, mostly empty expanse, filled here and there with rare islands of light and matter, all of it destined to disperse into nothingness. It's a bleak picture. It can make you feel small, insignificant, meaningless. If this is the universe, this vast, cold emptiness, then what does any of it matter? What do we matter? But I want to offer a different perspective. Because the emptiness isn't just absence. It's not just nothing. It's the reason everything exists. Think about it this way. Stars shine because the universe is empty. Nuclear fusion works because space is a near-perfect vacuum, allowing energy to radiate away efficiently. If space were filled with matter, if it were thick and dense like Earth's atmosphere, stars couldn't form at all. Their heat would be absorbed, their light scattered. The nuclear reactions at their cores would be disrupted. Planets orbit because the universe is empty. If there were significant resistance, if space were filled with gas or dust, orbits would decay in moments. Earth would spiral into the Sunday. Life would never have time to evolve. We exist because the universe is empty. The atoms in your body were forged in the hearts of dying stars, then scattered into the cosmos by supernova explosions. Those atoms drifted through the interstellar medium for billions of years before they came together to form our solar system, our planet, and eventually, you. If space had been full of other matter, those atoms would have been diluted beyond recovery. They would never have found each other. You would never have existed. The emptiness is what allows rare things to be rare. It's what makes matter special. It's what makes life precious. In a universe filled edge to edge with stuff, with no room for anything to move or change or evolve, there would be nothing interesting, nothing complex, nothing alive. The void is not our enemy. It's the stage on which the cosmic drama unfolds. It's the canvas against which the stars shine. It's the silence that makes the music of existence possible. And here's the truly remarkable thing. Despite all this emptiness, despite the overwhelming vastness of the void, the universe still managed to create us. Against all odds, in the tiniest fraction of cosmic space and time, matter organized itself into galaxies, stars, planets, and living beings capable of contemplating their own existence. We are the universe looking at itself. We are matter, to become conscious, able to wonder and question and explore. We are, in a very real sense, the universe's way of experiencing itself, of giving meaning to the void. Conclusion. So yes, the universe is cold. It's empty. It's vast beyond imagining. And it's growing emptier by the second. In the end, entropy will win. The stars will die, the black holes will evaporate, and everything will fade into a cold, dark equilibrium. But that's not the end of the story. Because right now, in this moment, we're here. Against all odds, in defiance of the second law of thermodynamics, we exist. We live on a warm planet, orbiting a stable star, in a quiet corner of a spiral galaxy, surrounded by an ocean of emptiness that stretches for billions of light years in every direction. That emptiness is part of us. The atoms in your body have traveled through it for billions of years. The light entering your eyes crossed vast stretches of void to reach you. You are connected to the cosmos in the most fundamental way possible. You are made of it. So the next time you look up at the night sky, remember, the darkness between the stars isn't just absence. It's possibility. It's potential. It's the reason anything exists at all. We are islands of warmth in a cold universe, islands of complexity in an ocean of simplicity, islands of meaning in a void that has no inherent purpose. And that makes us, and this moment, infinitely precious. Thank you for joining me on this journey into the void. May it give you a new appreciation for the rare and beautiful accident of existence.